Hello everyone, in this video we're going to be talking about the heap sort problem off of the sorting educator module. So heap sort is going to be one of our main log linear sorting algorithms, and by log linear we just mean that its average time complexity is n log n. This is the best we can think of so far for worst case sorting complexity. So this is one of them. It's very handy, and it's based on the heap data structure that you guys learned all about last week. So this should be a bit of a review, which makes it another fun application of using heaps. So the algorithm is like this. We're going to talk about more of what that actually means, but basically we're going to turn our array into a heap in place, and we'll demonstrate that. Then we are going to, while the heap size is greater than 1, we'll swap the first element and the last element, and we're going to reduce the heap size. We'll also show what this looks like, but basically we're sticking the elements towards the end of the list, and then we'll heapify after moving that, and then we just keep repeating until we have our whole list sorted. And I'm going to draw out what all of this means so it's a little easier to wrap our heads around. And then finally, we are going to be sorting a list of integers in ascending order. So we're going to get integers in any order, which you see right here. It's no particular order. And by the end of it, our integers are going to be from the smallest to the biggest number. The trick with this programming quiz is instead of letting you use any data structure you want, we are giving you the heap in something we call our array. And so this R array is basically just a regular vector, but we delete a bunch of the functions that you could have used to just say call standard sort on it or kind of cheese it and do any other method. So by giving you this class specifically, we're forcing you to actually do heap sort. And we're going to go through the steps for doing that in this class. But basically, you can't copy it or move it. You can't edit elements. You can only swap them. And then when you swap two elements, it's only going to let you swap if these cases are true. And we'll talk about, these are all we really need for it to work, but basically you can only swap with the left child because that's the index, or that's the index for a heap in a zero, or that is the index of a left child in a heap for a zero indexed heap. And similarly, this is the index of a right child. And then this is for the sorting at the end, which we'll get to. And yep, like it says, these restrictions will prevent us from using a sort algorithm other than heap sort. So what are we going to do about that? Well, let's draw out the sample input and think through the problem first. Try to follow this out and try to follow this algorithm, and then after that we will implement it in code. All right, let me move these windows around. So we're back. We got our drawing tablet set up. Let's go through this. All right. So what is our sample input? We are given a list with the following elements right here. I'm just going to draw them out. So we got 18, 25, 13, 2, 9, and 27. Oh, and there's one more, 0. So what does this look like? Right now, this is basically just any old list, but nothing's stopping us from just calling it a heap and turning it into a heap. So this is our first step. As we say up here, we want to convert the array into a max heap. And to do this, we're going to do what we call heapifying in place. In place just means that we're not using another data structure to like move the stuff into the heap. We're turning this into a heap where it stands. So how do we do that? Well, first of all, let's just treat this list as a heap by itself and see what happens. So let's say our root is 18. Let's say 25 is our left, 13 is our right. We have 2 here, 9 here, 27 here, and 0 here. And clearly, this is neither a maximum nor a minimum heap because this is smaller than 18, this is bigger than 8, or this is smaller than 18, this is bigger than 18, and that's not great. But as we know from when we did our heaps, it's really easy to turn anything into a heap by using either heapify up or heapify down. And you can use heapify up or heapify down to actually turn this into a heap in both cases, but one is a lot better. And you know, since this isn't Blue's Clues, I'm just going to tell you straight up, down is the better option. So if you're curious to the exact specifics of why this is better, you can read this very detailed, very long Stack Overflow answer. But in short, it's basically that when doing heapify up, what we would have to do is call heapify up from the very leaves and do that on every single node every time to get back to a proper heap. But with heapify down, what we can do is only start from the middle, starting at elements that don't have starting at elements that have children. So we don't have to heapify down any of these. Then we just heapify this down once, we heapify this down once, and we heapify this down twice. And if you actually run out the whole math and the geometric series, you end up seeing that actually doing heapify down starting from the middle is going to be a O of n operation. Whereas doing it heapify up, I believe would be, I want to say n log n? I actually don't remember exactly. This will provide more details, but long story short, heapify down is the better option. So how are we going to do that? Well, hopefully you remember from the heaps module, but just to demonstrate, what we're going to do is we are going to, starting from the first element with children, we're going to look at it, and we're going to say, okay, are any of its children bigger than it is? If so, we're going to swap it with its child, and then that's it. So, and we're going to keep doing that until it reaches the bottom of the tree or until it's in the right place. So we're looking at this, we see that 27 is actually larger than 13. So to get around this, we say, okay, we're going to swap these two. 13 goes away. We draw 27 right here. 13 moves here. Bada bing, bada boom. We did our first step. And so we don't have to go any deeper down now. I'm going to switch the color just so it's a little easier to see. Now we look at 25. We're already doing good here because 25 is bigger than 2 and 9. So nothing needs to change. So this is good. This is good. And finally, we look at 18. Now, 18 is smaller than both 25 and 27. And so if you remember from the heapify down operation algorithm, what we got to do is swap it with its larger child, because that is going to maintain the heap properties that all of the children are always bigger than the parent. Because if we were to put 25 up, for instance, and we had 25 here and 18 here, that would be okay for the left because 25 is bigger than 18, but it's not bigger than 27. So in every case, we want to always swap with the bigger element in, of course, a max heap. If this was a min heap, it'd be the opposite. But in this case, we have a max heap, so we are going to swap 18 and 27. We'll put 27 right here, 18 right here. And now we've turned our randomly sorted list into a valid max heap in O of n time. Now we can easily write this out in its new heaped format. So we got 27, 25, 18, 2, 9, 13, and 0. So now we have our lovely heapified list that we've made in place. And now we can start with the rest of the heap sort algorithm. So what do we have to do here? Well, it says while the heap size is greater than 1, we're going to swap the first element in the heap to the end of the array and reduce the heap size by 1. Well, what does that mean? Well, because we now have our stuff in a max heap, we can just perform an extract max operation on every single element in our heap. And in doing so, after putting the max, we put it at the back of the list right here. And then we keep putting the maximum element at the back of the list. And by the time we reach the start of the list, we'll have sorted the list in ascending order. So what does that look like? Well, first, we are going to extract the 27 and put it at the end of the list and swap the 0 out. So let's erase 27. Let's put the 0 back here. Let's make it red just so it's easy to see. Put the 27 here. Similarly, this 27 goes away. Now it's part of our sorted list. 0 comes up here. And obviously, 0 does not belong at the root of our heap because it is smaller than both of its children. So we can call that heapify down operation that we defined earlier, which is now very convenient that we're using that instead of having to maintain a heapify down and heapify up. And we can just put it to its correct place. So 0 is smaller than 25, and 25 is bigger than 18. So we go down the left, and then we're going to pick 9 because 9 is the bigger of the two elements. So our heap is now going to look like this. So we're going to have 25 as our root. We're going to have 9 right here, 18 right here. And then instead of 9 at the bottom, our 0 is going to have moved down, and we have 13. And so now we have a beautiful still max heap, but one of our elements is gone now. So now our heap size is only the remaining number of elements, right? So this is part of the sorted list. It's no longer technically part of our heap. So now our heap is just 0, 25, 18, 2, 9, and 13. So the heap size is 6. And now we just keep on doing this until we get to the end. So if I were to write the new heapified list, it would look like 25, 9, 18, 2, 0, 3. And then we have our sorted 27. I'm going to do it in black so it's easy to draw. And we have this. So we can do the same exact thing again, but we're going to put it at the end of the heap. Or we're going to put it at the end of the heap. So now we swap 25 and 3. 25, I'll do it in bold, comes to the sorted area. 3 comes right here. And now our heap is just these elements. So it's going to look something like 3, 9, 18, 2, 0. And similarly, we can just heapify down. So we see that 18 is bigger, so it should come up here. And we will heapify 3 down there. So we got 3, or 18, 9, 3, 2, and 0. And so you can do this so on and so forth until you reach the very end of the list. So eventually, you're going to end up with your list looking something like this, where it's going to be, let's see, 0, 2, 3, 9, 18, 25, 27. And you just keep repeating that process, and eventually your whole list is going to be sorted because your remaining heap section only has one element, and the rest of the list has placed each largest element in its proper place. So with that being said, this is going to have an n log n time complexity, as we discussed here. So because we built our heap in place, but each of the heapify down operations is going to be at worst O log n time complexity, because we might have to go down the tree, and it's a binary tree. So for each leaf, we're splitting the amount of searchable area in half. And in the worst case, we're going to have to go from the root all the way to the node, or from the root all the way to the leaves. And because we have n elements, it's going to end up being n log n. So that's great. That's pretty efficient. Now, how are we going to implement this in our code? I will pull up my editor and show you in just a moment. All right, we are back. I've moved my big head out of the way so you can actually see the code we're working on. I find it easier to work on this stuff outside of Educator, so I'm just going to use my editor right here. But we're going to be doing the same stuff, and we'll just paste it in after. Okay, so what's our first step? We need to convert the array into a max heap. And so this is just going to be basically the heapify operation that we talked about here already. We want to heapify in place. And to do that, we need a nice functional heapify down function for code. So let's start working on that now. So all this stuff is just the stuff we include. I'm just adding it here so my code editor doesn't get mad when I start referencing stuff in our array. So let us write our, let's write our heapify down function. Okay, so we want our heapify down to return void, because at the end of the day, we are just swapping things within the array. We're not actually able to edit anything because of the way that we set up the limits on our array. So we can just do that directly. So let us define our heapify down. And of course, it's going to need to take in our array, because we need to be able to swap stuff around, and we'll take it in by reference so it doesn't get copied and like not change anything. Furthermore, we're going to want this to be recursive, so we're going to need some kind of index in either case to know what we're actually heapifying down from. So that'll be an integer, and we will say in index, so we know, okay, from what thing do we want to heapify down from? And then finally, we need to know what the actual size of our heap is, because if you remember, when we get to this red part right here, only the stuff inside this counts as a heap, and the sorted portion doesn't. So we're going to be changing that heap size on each operation. So we will just say pass int heap size into this as well, and then we'll call this from heap sort when we need it. Okay, so what's the first order of business? There's basically three cases that we can run into when we're heapifying down. I will make this in a comment. Okay, so what's case one? In our first case, the thing at our index is going to be bigger than both of its children. So in that case, we don't have to do anything. We'll just do nothing, leave the heap as it is, not move anything around, because it's already fulfilling the heap property. So that's all good. Okay, what's the second case? Well, in case number two, we're going to see that the thing at our index is smaller than one child. Also, let me specify up here to just say, I don't know, do nothing. Then we're going to want to swap down with child. And so we're going to swap it down, and we're going to keep recursing until it's in the right place. So that's where the recursion will come in. And then finally, as we discussed in our diagram, if the index is smaller than both children, we will swap with the largest child. Cool. So let's actually write that in code. Because we're going to need to be checking whether the left or the right is greater a lot, let's just define two booleans now to handle that for us. And also, one other convenience thing, we're going to need to know what the left and right indices are, and instead of like calculating that each time with the 2i plus 1 thing, let's also just define that now. So let's say const int left, and that's going to be our index times 2 plus 1, and that'll give us the index of our left child. And we can do the same thing here. We can do say const int right, and that's equal to index times 2 plus 2. And so that's going to give us both of our children. Nice. Okay. And then let's also define our booleans for the comparison. So we'll say comparison results So we need one bool. Let's call this left. Sorry, let's have one bool. Let's call this left greater. And that's going to be equal to the whether or not the thing in the array is at the left child index is greater than the array at the right index. But wait, you might be saying, what about if it doesn't have a child at all? I didn't actually talk about that case, but if we look at this, for instance, if it has no children, we also need to account for that and not swap down. Or if it only has one child, we're going to swap with that child. If we try to do this, just like it is right now, we're going to run into a segfault. So there's a couple ways you can do this. You can add multiple checks. But what I'm going to do right here is just make this a little more complex. I'm going to use the ternary operator, which hopefully you maybe remember from Prog 2, but we'll talk about what that means. And we're just going to like have left greater also determine whether or not the child is even within the index. So just as a little refresher, for the ternary operator, it's going to look like this. So it's going to be some type of data type variable, and that's going to be equal to condition, and then value if true, or value if sorry, I'm losing myself. Value if false, right? So the thing, depending on whether the condition evaluates to true, if the condition here evaluates to true, var is going to be assigned to value of true. Otherwise, if it evaluates false, it's going to be assigned to value false. So we can do the same thing here. So left greater, we only want that to be, like, we only want it to do this check if there even is a left child to begin with. So how could we do that? Well, we can put our condition right here, and let's have this be our value of true. Let's have this be our value of false. So on what condition can we check if the left child is, or can we even check what's in the left child? Well, we're only going to be able to do that if the left index is less than the heap size. Because if it is the heap size, if we try to access our left, then we're going to try to access one pass into the array, get a segfault. We don't want that. So we ensure that we're only checking this if the left is less than the heap size. And if the left child index is just out of range of the heap, we can just return false no matter what, because we're not going to need to check that. We can do the same exact thing, but we can call this one right greater. We can say is right less than heap size, and then we will make it evaluate to that condition. Great. So now we have our comparisons. Now we need to actually figure out what we're going to be swapping. So again, we're probably going to be doing a lot of swap operations. So instead of like manually saying where that should be each time, let's just define the swap target index up here by itself, just so it's easier and the code is a lot cleaner to read. So we'll define our swap target up here. And now we can use these conditions we made in a pretty concise way. So first of all, what's our first case? Let's start with this one because that's going to override either of these cases. So if the index is smaller than both children, that would mean that both left greater and right greater is true. So we can just say if left greater and right greater, then what we're going to do is we want to swap with the larger of the two children. And just like last time, we can just use the ternary operator again to make this a little more concise. So I'll say swap target is equal to the is going to be equal to two or one of two values depending on how this condition goes. So we'll check the left child and we'll see, okay, is the left child's value greater than that of the right child? If it is, then we are just going to assign it to left because we want to make the left child the swap target. Otherwise, it'll be the right. Boom. Okay. So what if only one of them is greater? Well, now we can check both of those cases. So else if left greater, if only the left is greater, we know the right can't be greater if this is true. So if left is greater, we'll just say the swap target is left. And then if the right is greater, so else if right greater, then we are going to make our swap target equal to right. Okay, and so finally, if none of these are true, so it's in the right place, neither the left nor the right is greater, then we don't really want to do anything anymore. The node is in the place where it should be, we don't want to recurse down. We don't want to move anything. So let's just return out of our function now and end prematurely. So otherwise, assuming we made it past this point, we can actually do the swap. So let's say actually do swap. Now, what are we going to do? We can just call the swap operation that we define in here. So you can see that we have a swap function. It takes some index I and index j. If those indices match the conditions, it'll just swap those two pieces of memory. Otherwise, it'll throw this invalid index error. So let's just do our swap. So we can say r.swap, and we will swap the first index, which is going to be our index that we got passed in from the function, because that's what we're checking against. And then we will swap it with the swap target, which we assigned in our conditional up here. Great. Okay, and then finally, we might need to continue to do swapping, because obviously, as we saw in some of these cases, I guess we don't have it right here. Yeah, like for instance, for 0, we swapped it with 25, and then we also still had to swap it down to the position of 9. So to handle those multiple swaps, what we can simply do is just recursively call this function again. So now we can say heapify down again, and let's fill in the parameters. We're still passing in the array. The index is now going to be the swap target, because we're starting from there to see if it needs to get heapified down anymore. And then our heap size is going to be the same thing that we had passed in. So with all that being said, this is our heapify down function, and this will work for the rest of our coding. All right, great. So now it's time to actually implement our heap sort. So first of all, what do we got to do? Well, like we said before, we need to keep track of what the heap size actually is, because that could be different than the actual length of the array. So to start out with, let's just initialize our heap size, call it int heap size, and let's say that's equal to the array's size, because at first it's just our heap. We have nothing sorted, so let's say it's equal to array.getSize. Okay, so next, what do we want to do? Well, as we mentioned before, we're starting from the middle of the list and working back, because we only need to heapify down on nodes that have children, and we know that half of the nodes won't have children, right? So for instance, this has what, 7 nodes in it. 7 divided by 2 is going to be 3, and if we go to index 3, this is 0, 1, 2, 3. This is the first node. This is the first leaf node without children. So we can just start our heapifying down from half of the size of the heap minus 1. So for instance, in this case, size is 7. 7 over 2. Integer division is 3. 3 minus 1 is 2. So if we start 0, 1, 2, this is our first node that actually has children. So let us go through our thing in a loop. So let's do a quick little for loop. Sorry, this is the wrong code window. So we can define here. So let's say for int I, which is equal to half of the size of the array. So we'll say r.getSize. We could also use our heap size interchangeably here. It doesn't matter at this point since we're just heapifying, but I'll just do this for now. So for int I equal r equals for int I is equal to r get size over 2. And then we can say, just in parentheses to make this a little clearer, let me just do that, minus 1. Let me format this so it's actually visible. And then our condition is going to be, we want to keep doing this while I is greater than or equal to 0. So it goes through all the elements. And then finally, after each run of the loop, we want to decrement I. So now we have our custom for loop iterator. Great. And all we have to do is call heapify down on the elements. So great. Our array is still R. Our index is going to be whatever I is. And our heap size is going to be the heap size that we got. I'll just call it heap size for that. Again, in either case, you can use heap size or r.getSize. This is going to change ending here. So first, we are going to heapify in place. So that's what we're doing now. Now we need to actually start extracting our max again and again and again and again. So let me just number this. Great. Great. So now we need to go through this part of the algorithm. So while heap size is greater than 1, swap the first element to heap to the end of the array and reduce the heap size by 1. So while heap greater than 1, swap to end. Okay, so what are we going to do about that? Well, pretty easy. All we got to do is make a loop, and we could do this just straight up with the condition he said. So that's easy. Let's do that. While heap size is greater than 1. And everything will happen that we care about in this loop. Great. So what are we going to do? We simply need to swap the thing from the first index to the last index in the heap. So what we can do here is we can say we are going to call r. Oops, sorry. Let me make that visible. What we are going to do is call r.swap, and our first index will be 0 because we're always swapping from the thing at the beginning of the list. And our second index will be the thing at the end of the heap. So remember, if you use actually heap size as the index, that's going to be 1 too large. So we're just going to decrement heap size. And because we're using the pre-decrement operator, this is going to say, okay, swap with 0 and whatever 1 minus the value of heap size is. And at the same time, this is going to subtract 1 from heap size. So this is handling the swap. This is great. And then now we need to actually fix whatever we swap down. So our new thing ends up at the top, like when we replace the 0 up here, and we need to heapify down starting at that 0. So we can just call heapify down from that 0. So we can do heapify down. We can pass in our array as normal. Our index will start at 0, and our heap size will be whatever we had before. Groovy. And after this should be all you need. Assuming I didn't make any silly mistakes when looking up my notes, this is all you really need for this function. Once you have your heapify down written, the heap sort itself is super duper quick. So let's see if this works. I'm going to take this whole chunk of code. I will copy all of this, paste it into here, and let's see how we do. I'm going to extend this window a little bit. Oopsies. Sorry, I'm having some trouble. But okay, our window's extended. We have our code right here. We have the problem. First of all, let's run it and see if it compiles. Our compilation was successful. Great. Let's submit and see how we did. And there you have it. We passed all of our 8 tests, and we have implemented heap sort using our special array class. Thank you guys so much for watching.